This is lecture 2 of our course EEE 4705. In this lecture, we will try to understand the very basics of assembly language for 8051 microcontroller. So previously in the last semester, you learned about assembly language, but which was specifically for 8086 microprocessor. So what we will see, whenever it comes to low-level language like assembly, actually the language is closely related to the architecture of the device itself. Like we have this microcontroller, right? So previously whatever we have learned in 8086, they may not match totally with the one we will learn here for 8051, because whenever we are talking about assembly language, we are directly trying to manipulate registers to do something, so very closely related to the architecture of a particular computer. So we will try to understand all of those things in this lecture. I mean the very basic things of the structure of assembly language. So also here the same book, throughout this semester I will suggest you go through the first book from Majidi for our course syllabus, as well as for doing good in the exams, because most of the things or almost all of the things will be from that book, but sometimes I can add some additional resources through the help of some other books like the second one we have here. But if that happens, obviously I will provide you those resources through lecture slides and also lecture videos if possible. Okay, so yeah, let us start this lecture. So before we start, the first thing we need to understand, the memory map or the registers and other memories we have in our microcontroller or microprocessor, these are very much important when we are trying to understand assembly language, because with assembly language we are trying to manipulate or move data, different kind of manipulations on those kind of memories are being done in assembly language. So by looking at assembly language, we look that with each and every line we can understand how these values are moving from one place to another, from one register to another. So understanding the behavior of register, the characteristics of registers, the features of registers are very much important whenever we are trying to learn assembly language. So how we plan to go through this course is, parallelly we will try to understand the behavior of registers, also understand assembly language as well. So how assembly language can be used to manipulate those or use those registers, we will try to learn parallelly at the same time. So here you can see the overall memory map of 8051. So I know it may seem very difficult and complex right now. Obviously we have a lot of registers and memory here, but what we will do initially from this chapter is try to understand just some very basic common types of registers, how they work, how they help us to do different tasks. We will try to understand. So here you can see this portion here, this is actually the internal RAM. Our original 8051 had 128 bytes of RAM, so this is that 128 bytes of RAM, and we will try to look at the details of this one in this particular lecture. And then we also have a thing called SFR, special function register. So after this internal RAM we have another 128 bytes of these special function registers, who the address of that starts just after the address of internal RAM, but that doesn't mean like they are adjacent to each other. The physical location of each of the registers we have here can be in different places. That doesn't depend upon the address of this particular registers, right? But as you can see, we have a lot of registers here. So we will try to look at some of them in this lecture to understand how they work. and then our internal ROM. So original 8051 had 4K bytes of RAM, so we can see that. Also details of that will be discussed later on in this lecture. And also we have another one, you all know about this particular register called program counter. So yeah, so this is the overall memory map of 8051. One by one, maybe after we go through the whole semester, maybe we will learn about all of the registers we have here, all of the memory we have here at the end, right? So as I said, we will start with just some very basic types of registers of 8051. So I think in the first lecture we discussed about a term called word length. So word length, so we said that, like for example, for 8051 we call that a 8-bit microcontroller. This is because 8 bit of data can be processed at a time with this kind of microcontroller, right? So that is the word length of 8051 for our case, right? Now based on this word length, the registers are also designed for a particular microcontroller. So as you will see, in most of the cases, most of the registers we have in 8051 will be of 8 bits, and all kinds of data manipulation will happen in terms of 8 bits. So if we have a data that is more than 8 bit, it will be divided into 8 bit chunks, and then it will be moved from one place to another. So that is the idea. So here you can see some examples of these 8-bit registers. Like we have register A, register B, then R0 up to R7. So first of all, register A, this is I think one of the most important registers in any kind of CPU, because these are called accumulator. So we will try to learn about that, but I think also from your knowledge from third semester in SAP 1 we learned about accumulator or register A. So all kinds of arithmetic operations were done with the help of register A, and after that arithmetic operation the result was also saved on register A. So that was the idea. So it has a bit more responsibility compared to the other registers, as you will see. So and all the other ones we can see here, the register, these are just general purpose registers, just to store some data and move data from one particular register to another register. So this kind of things, okay. And here we have some example of 16-bit registers. We have a few in our 8051 of 16-bit registers, but they have some specific tasks to complete actually. Like for example, we already know about program counter. So that was 16-bit register because we could actually address up to 2 to the power 16 different locations in our memory, right? That is ROM, right? So we said that because we had program counter of 16-bit as well as 16-bit address bus, as a result, because of that, we could actually access from our ROM. If this is the ROM, let's say for example ROM, we said we could actually access from 000H up to FFFFH. So if I say these are the locations, in each of the locations we can have 8 bit of data. So basically, as we have 16-bit register for program counter, we can actually address up to 2 to the power 16 different locations in the ROM. And what is the purpose of program counter? For pointing to the address of the next instruction to be fetched. That was the idea, right? So initially it starts from 000H, and after all it tries to increments to points to the next instruction to be fetched. We learned about that in the previous lecture, right? So yeah, now let us try to look at some very basic types of assembly instructions to understand how using this kind of registers we can manipulate 8-bit data. So we will first look at move instruction. So for move instruction, basically the syntax is like that. So we will have move, then the destination, the register where that data will be saved, and the source where the data will come from, right? So this is the basic idea. Like for example, we can have this kind of line of code here. So what we're trying to do here, from RO register or R0 register, we are trying to move a data into register A, right? So whatever data is saved currently in this particular register RO, that will be moved to register A. But basically what we are doing in reality is just copying the data. So that means nothing stored inside RO will be modified. It will be intact, but that will be copied into the location of register A. That's the idea, right? So after execution of this particular line of code, both of the registers, register A and RO, both will have the same data. Now let us just look at some of the examples of how this kind of move instruction can look like, right? So I think line 2, line 4, line 6, line 10, these are all understandable, just like the previous one in the previous page what we have seen. But this is different, right? This one is different and this one is different. So by using this hashtag, what we are doing, we are trying to say that this value, this hexadecimal value, try to move or store that onto register A. Instead of, from one register to another moving data, what we are doing, we are directly calling a value and putting that onto a particular register. So that is the idea. So basically whenever we are using this kind of hashtag, this becomes a value. And this is important because if there was no hashtag like that, that would actually could mean different thing. That would be a valid instruction, obviously, no problem. But the problem is if you write, move A, 55H, the difference is now we are saying that from RAM location 55H, whatever that is saved on that particular location, move that to register A. That is the instruction here. So there is a difference between these two instructions. Try to remember that. Now using this type of lines of code, we will try to understand some of the rules we have to follow for assembly language. Like for example, the first question that can be asked is whether assembly language is case sensitive or not. So case sensitive means if you write a code in uppercase letter, then write this code in lowercase letter, will that make any difference or not? That is the question, right? So in assembly language, it doesn't matter. So if you write this whole code with lowercase letters, it will execute exactly the same and your result will be identical. So now, as I said, we will try to look at some rules. What are the things to follow for writing assembly language through the help of this particular type of instruction called move, right? So first of all, we already learned about that. We have to use that hashtag sign to make sure that we are trying to move a value. Like this is the 23H hexadecimal value we are trying to move, not a memory location, right? And also try to understand that for representing hexadecimal values, we use a H at the end of each number. But for the case of decimal, you see we don't have any kind of H or anything written here. If you want to represent a binary number, obviously you have to write a B at the end. So that is the idea. Then next, look at line 5 here. For this one, the value is F9H. This is a hexadecimal value, but because it starts with a letter called F, or any kind of letter like A, B, C, D, E, F, these are the possible letters that can come for hexadecimal value, right? If that happens, then we have to start with 0. Otherwise the assembler will cause some problem, right? So because it can be interpreted as label. What is label we will learn very soon in this lecture, but if you don't give the 0 in front of f, it may be considered as a label that will cause some problem. So that's why we have to put this 0. The next, we know that always we are trying to manipulate 8-bit data, right? All of the registers are of 8-bit size. So that means the data we are trying to save onto these registers should also be within that limit, within 8-bit, right? So if you look at line 4, you will see that the value we are trying to move to register A, it is not 8-bit, more than that, right? So it will cause some problem. The assembler will show that this line is not correct, it will cause some error, right? So always we have to put value that is less than 8-bit for valid instruction. Now next, let us try to understand add instruction. So similarly, like mov instruction, it is the structure is almost same, but here we are trying to add two values, right? So the one of the values will come from the source, and that will be added with already what is contained inside of register A. So register A plus source will be actually the result, but that result will also be saved onto register A, or which is called accumulator, right? So that is the main idea of register A. So that is the main idea here. Whatever addition happens afterwards, the result of that addition should be stored on register A, always register A. That is the thing we have to remember for this kind of instruction. So here in this example you can see we are trying to add two values. So what we have done, we have first moved the first data 25H onto register A, then again moved another value onto another register called R2, then we have added R2 with the values of A. So finally 25 plus 34 hexadecimal value, these two addition of that will be saved onto register A. So result I think should be what, 59H, right? So this instruction can be written in three different ways, as we can see here. So like this is the first example we have seen from the previous page, right? It can also be written in this way if we want. So what we can do, we can use two different registers to store the data, then first move value 0 onto register A so that it is empty, then add R5 with that, then add R7 with that. So after execution of all of this line, we are going to get the same result, 59H. Another thing what we can do, the most efficient way I think, is without the help of this kind of registers, we can directly move data. So we will move the first data onto register A. So register A already have 25H. With that, try to add 34H. So afterwards, we are going to have 59H inside of register A. So that is the idea. So this kind of method, this kind of data are actually called immediate data, and this kind of addressing is called immediate addressing. So in the later chapters, when we will discuss about different modes of addressing, we will look at this one as well in detail, right? So but you can see we have different approaches for doing the same thing. But for all of the cases, one thing is fixed, that is the destination for add instruction should always be register A. So A register will always contain the result of this arithmetic operation. Well, now we will start with the very basic structure of assembly language with this example code here. But before that, I think we should understand the significance of assembly language, why we are trying to learn that. Like for example, if we talk about 8051 or 8086 or any kind of computers, what they basically understand is just machine language or binary values. But we still opted for, or we have actually invented assembly language then, so that we can understand properly for our convenience. It was invented, right? So how each of the registers are being accessed, how they are being manipulated, everything can be understood by looking at assembly language, right? Now we have many higher level language where we don't even have to worry about how these registers are being accessed or manipulated. But if we look at assembly language, we will understand the architecture properly of a given computer, right? So that's the significance of assembly language. And also, if we talk about this course, we are trying to understand the architecture of 8051 through the help of assembly language. So in any assembly language, if you look through the code, what we will see is each line is either a instruction or a statement called directive, which is actually called assembler directive, right? So what is instruction? We already have seen two examples of instructions like move and add. So these are instructions basically. But assembler directives are not actually instructions. These are basically instructions for the assembler, right? So basically, whenever we have an assembly code with a program called assembler, we try to convert that into machine language, and that machine language is actually understandable by our machine or 8051 or any kind of computer, right? So for that process, assembler gets some directives. So these are actually called assembler directives. These are not specifically instructions for the microcontroller. So after conversion, these will not get converted into a data and will not be saved into the ROM location. So these are just instructions for the assembler so that they can understand how to actually properly convert the code. That's it. For example, let us look at this first line, org0h. So org0h means the origin should be at 0000h location, right? So whenever the assembler tries to convert this code into machine language, it will understand that it should start storing the code we have from 0000h location of ROM, right? So that's why we have this assembler directive. So this line will never be converted into a code and will be saved onto the ROM. Rather, it will just explain or command the assembler that afterwards, whatever you see, you should start storing those from 0000h location, or at least make a machine code that will do that. Okay, so that's how it works. Also, if we look at this last line end, this is also another assembler directive. So because of this line, assembler will understand I have to stop here, the code ends here. So if anything is written here, it will not be converted into machine language. That's the idea. So that's why these are not intended for the computer or 8051. These are intended for the assembler, right? So we understood assembler directive. Now let us look at instruction. So we have different instructions available for 8051. The general syntax structure should be like this. So we will have label, mnemonic, then operand, and there can be also comment. So whatever you can see here in third bracket, these are optional. So we can have any instruction without these components here, but we must have a mnemonic. So what is mnemonic, what is opcode? These are important, right? So before that, I will go to the next page and talk about some of the things to understand mnemonic, opcode, this kind of thing. First of all, if you have completed the first experiment, I think you know that we have a software called Might51. Okay. And with that particular program, what we did, we could write any kind of assembly language, assembly code like we have here, and we could actually save that onto our computer as .asm file or assembly file, right? Afterwards, we could build from this assembly file, and we actually got 3 different files from this assembly file, right? After building, one of them was called dot hex, another one was called dot lst, and the last one was called dot dev, right? So this hex file, this was the original machine language file, you can say, which was later burned onto the ROM of 8051 for our code to work, right? So this was the main thing we needed from this assembly file. But also you are going to see that we had list file and this dev file, right? So this .lst file, if you try to open that through the help of any kind of notepad, you are going to see a information like that. Okay, so this is the information we are going to see, and here what they're trying to say is, this is your code you have written in assembly, and this is the converted machine code from that. Okay, and these are the memory locations of ROM. In this memory location, in this way, the data are saved, the machine codes are saved onto the ROM of 8051. So that is the idea, right? So now, what is opcode, what is mnemonic, what is operand? Let us try to understand that, right? So let us look at these two lines here, right? So this is the assembly language and this is the corresponding machine language of this particular line, right? So for this particular portion, the first two values, 7F or this 8-bit, this portion is actually called opcode, right? So this is the actual instruction for our 8051, and from this 7F we are getting this portion move R7, right? So basically 7F means a value has to be stored or moved into R7 register. So for that instruction we have this opcode 7F, right? And 34, this 34 is coming because of this 34 value. So we are saying that 34 value should be saved onto register R7. So that is the idea, right? Now here for this machine code, this one is called operand, just 34. Okay, but for the case of assembly language, only this portion is called mnemonic. Okay, and both of them, this one and this one, these are called operands. So there is some difference in definition whenever we are talking about operand for machine language and assembly language, right? So that you have to understand. Now let us again go back to our previous page. So here we have the general syntax of assembly instruction, right? So we have mnemonic and operand. So for this particular line of code, this is the mnemonic and we have two different operands, and we also can have label and also can have comment, right? So for writing comment, you can just start with a semicolon and write any comment if you want, but these are not part of the instruction itself. And also label, later on we will actually understand what is the purpose of using label. Maybe right now we don't have enough facility to understand, but label field basically allows the program to refer to a line of code by name. Okay, so if you have written a particular line of code here using this particular label, you can actually refer to that line, and elsewhere in the code you can use this particular label here to jump to this particular line of code. So that is the idea. And sometimes also we will see that we can actually define a particular variable, just like our C programming, similar to that, can be done using label also. So many things can be done, but maybe with example, if we try to explain, that will be easier to understand. So for now we will skip it, right? Now, as I talked about the list file, so let us try to understand more here with the help of list file, how actually a code gets executed in 8051. So these are the memory locations starting from 000H. So these are hexadecimal values, these are the opcodes, right? And what you're going to see is that for machine code of 8051, each of the instruction can be of either 1 byte, 2 byte, or 3 byte, right? But the first byte always will be reserved for the instruction itself. So here all the first bytes you can see, these are actually denoting a particular type of instruction, right? For example, this, for this one, this is the instruction, right? So in this way, first byte is reserved for the instruction, and after that, whatever we can see, these are actually the values or data or operands which we are trying to manipulate, right? So here from this assembly code, everything starts from 0000 location, because we have written org0h. So you see, from 0000 location we have got this machine code, right, from this assembly language, which is of 2 bytes. Because we have 2 bytes of data for this instruction, that means we need 2 different locations. Each of the locations inside the ROM of 8051 have 8 bit of space. So that means 70 will be stored on 0000 location, but 25 has to be saved on 0001 location, right? So that's why for the next instruction, this one we have to start from 0002, right? So in this way, you see, after each of the instruction, if the instruction is 2 bytes, that means it will take 2 adjacent locations from the ROM to save that. And for this case, we don't need 2 bytes of memory. So that's why after 6, directly we get 7. At the same time, our program counter PC also has to increment properly, so that we can properly fetch each instructions, right? So basically what happens whenever, you know, we start our program counter will start from 0000, right? So that will be the data initially saved onto the space of program counter. So then this data will be sent to CPU. CPU will actually send this address through the address bus to the ROM and fetch the data that is stored on 0000 location, which is, you know, 70. Am I right? So after that, this 70 will be sent to the CPU with the help of data bus, and our CPU will try to decode this data with the help of instruction decoder, right? So it will understand that into R5 register we have to move some data. What data? That is actually stored on the next location on the ROM, right, which is 0001. So in this way, it will understand 2 things: what is the instruction, and also what is the size of that instruction, which is 2 bytes, right? So because it knows the length of the instruction, it can also increment the program counter accordingly, right? So for this case, obviously the program counter should increment by 2 for the next instruction, right? So in the meantime, obviously execution of this instruction will happen, but also the program counter will be incremented by 2, so that whenever the time comes for getting the next instruction or fetching the next instruction, program counter should have the correct value to fetch the next instruction. So in this way, the program counter can either increment by 1 or 2 or even 3, based on the situation, based on the size of the code. The machine code we have can be of 1 byte, can be of 2 byte or 3 byte even. So how it can be 3 bytes of length? What you have to understand, always the instruction is of 1 byte. So 8-bit instructions are fundamental to the architecture of 8051. That means we can have 2 to the power 8 or 256 different instruction for 8051. In reality, we have actually 122 instructions made for 8051. Basically these are opcodes, right? We have 122 opcodes made for 8051, and after that, after this byte, we can have 2 bytes of data. Like for example, right now we are trying to manipulate only 8 bit of data, but there can be situations that we are trying to manipulate a data that is 16 bit or trying to get an address which is of 16 bit. That is possible. Like we have registers like DPTR, right, data pointer. So for that case, we are going to see that the operand portion is taking 2 bytes of data, because we are trying to move or manipulate a data that is 16 bit of length. So that can happen. So let us try to understand line by line what is happening in the code. So basically we are trying to move data to R5, then move data to R7, then we are trying to move something to register A0. So we are basically looking at one of the examples we saw earlier, just like that. So we are trying to add different values that are stored on different registers. So afterwards you can see that here we have written this, here colon short jump here. So this is another instruction we will learn very soon, but this is just an example of infinite loop. So what happens is this is the label here, but this is the instruction. So whenever you have short jump basically says that whatever label you have here, go to that line. So it will go actually at the same line here, and after coming here it will again get the same command, short jump wherever you get the label here. So in this way, in this line, it will try to do an infinite loop basically. So sometimes it is helpful, because sometimes after doing some executions we want to just keep our microcontroller stalling, right, without doing anything, just keeping the result it has. For those cases we have infinite loop, right? So, and also end is just directive for the assembler. So afterwards, if we had any code, assembler would not convert that to machine language. That's the idea. Okay, so this is the overall idea of machine language and assembly language and this list file. We talked about different registers so far. Now let us talk about the ROM. Like the original version of 8051 we discussed previously, that can be 8089C51. These particular versions of 8051 has only 4K bytes of ROM, if you remember, right? So that means the starting address of that particular ROM would be 0000, and the ending address or the last address should be 0FFF. So how that happens, how I remember that? So I have a silly approach I use always, to understand, or from these memory addresses, how can we understand what is the amount of memory for this particular ROM, right? To do that, what I do, like you can say that for 0FFF, 0 basically means this is the last address. That means for this particular location we can only have one possibility, 0, right? So one possibility here. Then for this F we can have 16 different possibilities, right? So 16, so multiplied with 16 we can say. Similarly for all of this we can say 16. Now what you can do, you can convert that to 2 to the power 4 multiplied with 2 to the power 4 multiplied with 2 to the power 4, and finally you are going to get what, 2 to the power 12. And you should say bytes because what, because each of the locations we have here are of 8-bit memory, right? So that's why bytes. And we can also write it in this way, so 2 to the power 2 multiplied with 2 to the power 10 bytes, which is what, this is 4, and 2 to the power 10 can be written as kilo, right? So 4k bytes. So, or we can say for this particular memory type the amount of storage is 4k. Similarly, if you try to do the same thing for this one, the first value is 3. That means the possible values are 0, 1, 2 and 3, and 3 is the 3FFF is the last location for this particular ROM. So that means here we had written 1, this should be what, 4, right? And then we can also multiply 4 here. Similarly, in all of the cases we have to multiply 4, and this will be what, 16, right? So for this case the total memory, overall memory is 16k bytes, and for this one we have to multiply with 8 because 0, 1, 2, 3, 4, 5, 6, 7, we have 8 different possibilities. So this is one silly approach I do to understand how much memory we have for particular ROM. Hope that helps you. Now we will try to learn even more syntax and behaviors of assembly language. So one of them is, data type. So what are the data types available? Actually there are different data types available for 8051, but most prominently we used this one called defined byte or DB. So this is just 8-bit data definition. So as everything is described in terms of 8-bit in 8051, so this is the most helpful one, and we can represent binary, hexadecimal, decimal or even ASCII values with this kind of variable, basically data type, right? So DB. So how to do that? This is quite easy to understand, but there are some specific details you have to understand. Like what we are doing using DB, we are trying to write some value onto a memory location of 8051, basically ROM, right? So here if we try to understand from line 1, so org 500H means start from 500H and try to execute the next line or try to save the contents of the next line starting from 500H. So in the next line we have data 1, which is 28 in decimal, right? So in 500H location we have to actually store 28 in decimal, right? So that is the instruction. So maybe we will talk about the label later on. Just try to understand this thing. So in 500H location we have stored this one. If we go to the next line, this value will be saved on the next location, which is 501, and in the next line 39H it will be saved on the next location, which is 502. So we are just writing the location. So this is 500H, right? This is 501H, and this is 502H. So then we have another org statement. So they are saying now start from 510. So here this should be stored on 510H. But wait, there is a problem, because this is not decimal, hexadecimal or binary values. All the values you saw earlier, like this one or this one or this one, all of them were within 8-bit, right? So obviously because DB is 8-bit of length, so there was no problem. But for this one, because we have double quotation here, this is representing a ASCII data. So all of the characters are ASCII characters. We have 4 characters like that. Now what is ASCII? ASCII basically is, for each of the characters we have in keyboard, we have an equivalent 7-bit binary data. Okay, so whenever you press a key onto the keyboard, basically that 7-bit data is going through from the keyboard to the PC, right? So for each of the keys we have a unique 7-bit combination basically of binary value, right? So what we have done currently, like because we need 8-bit length, so that's why the last bit, the most significant bit, can be 0. So we have 8 bits of chunks for each of the ASCII characters. Like for 2 we have a 8-bit combination, for 5 we have a specific 8-bit combination for ASCII, right? So here we don't have 8-bit, rather 4 multiplied with 8-bit or 32 bits, right? So how actually this gets saved? That is the question. For this case, what happens is it will start from this one, this particular value, ASCII value, then go to this one, and sequentially it will save starting from 510H location. So what we are going to see, like 510H location will be saving 2. Okay, there will be obviously a 8-bit binary combination for that, which will be saved actually, not 2 in double quotation. You understand that? For 511H, 5 will be saved, ASCII 5. So basically a 8-bit combination that is representing the 5 ASCII value basically, right? So in this way actually all of the values 9, 1 will be saved sequentially. Then it will come to 518H, right? So again this is another data with ASCII characters. So for each of the characters it is taking 8 bits, so each of the characters will be stored onto one of the locations of RAM starting from 518. So this will be stored on 518, this will be stored on 519, this will be stored on 520, 521. If there is a space here, that will be also considered as a ASCII character, so it will be saved onto a particular location, but sequentially one by one, right? So even though DB is meant to be 8-bit data type, but that means all of them will be considered as separate DB, and they will be located or stored on a specific location of ROM, right? Now let us come to these labels. Whenever we say these things, data 1, data 2, right? So basically what they're doing, if we want to call these values, this 28 in decimal elsewhere in the code, we can actually call using data 1, no problem. We can use data 2 to call these values, just like we have, for example, in C programming we can write int, maybe we can name this variable as IoT is equal to 9. So whenever we say IoT, this basically means 9. So that is the definition of having this kind of data type, int, float, or this kind of things. We have variable to call them. So these kind of labels are helping us to do the same thing. But let us look at this one. If I call data 4, then which value should come? Because this is not 8-bit value, rather more than that. So if I call data 4, 8-bit data should come, and that is what happens. So by data 4, basically we are just representing this one, the first value we have here. Okay, so if you write elsewhere in the code data 4, what we are trying to call is 2, not 5, not 9, and 1. But what you are going to see later on, maybe in next lectures, is using these labels for DB, we can actually access all of the values with the help of data pointer. You are going to see that, but for now we don't have to worry, just understand the definition of DB. Okay. Another question, I think one of the students asked me whenever we talked about this data type in the class, is if this decimal value is more than 255, basically if it exceeds 8 bit, then what will happen? Is this valid? So the answer is not. I think I gave the same answer there also, but later on I verified myself and I saw that actually if you give a value here which is more than 255, any value that is more than 8 bit, it will cause some error, so assembler will detect error. Okay, so we have to remember that. Okay, now let us look at different kind of assembler directives. We already know the definition of that, and also we learned about org and end directive. So there is another one called EQU or equate. So general structure is kind of like that. So we have the label, then EQU, and then the value. So basically using this label now we can write the code elsewhere, and just by giving this label we can recall that value, but it will not occupy any kind of memory. That is the benefit of that. So there is no storage needed for this kind of syntax, this kind of assembler directive. This is just for the assembler to understand. So what happens basically whenever assembler tries to convert this code into machine language, it will just look at this label and look at this value, and wherever it gets count elsewhere in the code, it will just replace that count with the value 25. That is the idea, but it will not go to the ROM of our 8051. So what is the benefit of this kind of approach? So basically if you have a code where you have used this particular value in multiple places, in multiple lines of the codes, and afterwards after calibration you want to change the value somehow, so you don't have to manually change all of them. You can just change the value here, elsewhere it will take the effect with the help of assembler. So that is the benefit basically. Then final thing, like for this kind of labels, the labels we have seen, there are some rules to follow how to write. First rule is obviously in the code all the labels should be unique, otherwise they will be considered as same. Then to write any kind of labels, you can use numbers, you can use alphabetic characters, then you can also use some special characters like question mark, period, underline. These kind of things are also allowed. But the thing is, whenever you write a label, you should always start with the alphabetic character. It cannot be a number. And also there are some reserved words for assembly language, like for example for instructions we have move and add. If you try to use those to write a label, obviously they will be misinterpreted, right? That will cause some problem. So that's why these reserved words cannot be used. Okay, now we will look at a special kind of register called program status word. Again here this word term may confuse you, because initially when we started the course we said that word means 16 bit, but this is not actually entirely true. Word basically depends on the architecture of the machine, right? So like we said the term word length. So for our case, for 8051, the word length is 8 bit. So all the things are are represented in terms of 8 bit or multiples of 8 bits, right? So the word length of 8051 is 8 bit. So that's why this program status word also means a 8 bit register for program status, right? Not 16 bit. So for different microprocessor or microcontroller, this word length can be different, and for that you are going to see the register, different bus architectures will be done in that way. Okay, but this particular register is quite important for 8051 because this is a kind of flag register. So whatever changes is happening, sometimes in our accumulator register A, and also some other cases it can be different register, but basically based on those condition there will be some flags raised here. With the help of those flags we can actually make some decisions, right? So this is very important. In total the length is 8 bits. This is the least significant bit, this is the most significant bit. So if we say this is bit 0, from there this is the bit 7, right? And in the assembly code we actually call them by this kind of name. So psw.0, psw.1, in this way we can actually call them or modify them if we want, right? Well, later on we will see how to modify them, but one by one try to understand them. And another thing I think we haven't talked about this, but the address of this particular register is D0H. So actually this is one of the special function registers. So we know that from 0 up to 127 these addresses are actually of the RAM, right? This 128 byte. After that from 128 to 255 these locations are actually reserved for the special function register. So this is one of those addresses. If we want to actually fetch all the data, all 8 bits together, we can actually use this address. So not important right now, but here among these bits, some of them are called conditional flags. So based on the condition, based on the behavior of register A or some other register, you are going to see that these particular bits change their values. Okay, so what are those? This CY, carry flag, AC, auxiliary carry, then there is this overflow flag, and we have this parity flag. So first of all we will try to understand these things, okay, these particular bits. So let us start with carry flag BSW.7. So basically whenever you are trying to do some kind of arithmetic operation like addition or subtraction, there can be situations like from the last bit or most significant bit of register A, we have an extra bit coming out to bit 8 basically. Understand that we are representing everything from bit 0. So that's why this is actually 9th bit. So we are saying if anything comes to 9 bit as carry from the 8th bit, or also we can say from bit 7 to bit 8, this kind of situation is actually carry. And if that happens, this carry flag is set, so it will be 1, otherwise 0. So that's the idea, very simple to understand. Then let us look at auxiliary carry. So for auxiliary carry, similar kind of, so if carry happens but from bit 3 to bit 4, if after any kind of arithmetic operation, addition or subtraction, whatever, the resultant is always seen in accumulator or register A. In register A, if a carry is happening from bit 3 to bit 4, so that will be auxiliary carry, and this flag will be set. Okay, so generally this is helpful for BCD operation, because for all the BCD characters are of 4 bits, so for those cases it is helpful. Then let us look at overflow flag. This is quite complex for this moment to understand. Whenever we go to that particular chapter to discuss about overflow, we will talk about that in detail. But basically what is happening, whenever you have signed arithmetic, okay, in general all the unsigned arithmetic will happen for the total 8 bit, okay, from 0 up to 7, all of the bits are used for arithmetic operation. But whenever you have an operation where we are using signed arithmetic, the last bit or the most significant bit will be used for the sign, plus or minus, right? So the rest of the 7 bits are used for arithmetic operation. So if that happens, that after any kind of arithmetic operation, any overflow, if any overflow happens from the 7 bit to this 8th bit reserved for sign, then we say overflow has happened and overflow flag will be set, right? So that is the idea. But arithmetically, if we try to understand, there are some very complex details to understand. So whenever we talk about that in the specific chapter, we will go into the detail of that, how that happens. But for now, we can skip that, no problem. Now the last one, parity flag. This is the most easy one compared to the other ones. Basically, we will, after any kind of arithmetic operation, we will look at accumulator or register A and count the number of ones we have. If the register A has odd number of ones, then we say parity should be 1, otherwise 0. Okay. Now these are the 4 registers we talked about, which are conditional flags. So based on the condition of register A, these flags can be raised or cleared. But we have these 2 particular bits in PSW. These are not reserved for anything, so these are just user defined bits, so we can use them as a flag and we can define those ourselves on what condition they should be set and reset. So one of them is this PSW.0, also called F0, and this actually doesn't have any kind of name, but this is also PSW1. So you can call through assembly language this particular bit as PSW.1. So that is the idea. So we have talked about most of them. I think we still have these 2 to discuss about, RS1 and RS0. So these are actually register bank selector, these 2 bits. But to understand these 2 bits, we have to understand about register bank, which is part of RAM. So in this lecture, when we will learn about register banks, afterwards we will come to this RS1 and RS0 to understand how they work. Now one example, just one very simple example to understand how carry, auxiliary carry and parity flags can be set based on some any arithmetic operation, right? So here they're saying that after this execution of 2 lines, what will be the condition of these 3 flags, right? So what they are saying is just try to add them together, right? So move to register A this value. So in the second line, register A already have 38H, and with that we have to add these 2 values. So we are basically just trying to add these 2 values, and the binary equivalent of these 2 values are these 2. So let us try to complete the addition. So 0 and 1, if you add them together, it should be 1. Then 0 and 1 again 1, 0 and 1 again 1, 1 and 1. After you add them in binary, the result should be 1 0. So we take the least significant bit 0 and most significant bit will be taken as carry here, right? So now we have 1 and 1, so again 1 0, 0 should be here. We again have another carry to keep it here, right? So 1 1 1, 3 ones equal to 1 1 in binary, so the LSB 1 should be kept here and we can have a carry here, right? And now we have only 1, so and these 2 zeros should be equal 0. So this is the result, right? So after this execution of 2 lines, register A will have this content, right? And what should be the condition of CY carry flag? It should be 0 because we don't have any overflow or carry from 8th bit to 9th bit, right? And for auxiliary carry AC, we know that from bit 3 to bit 4 we have a carry, right? This one. So we can say AC should be equal to 1, and parity is defined based on the number of ones we have. So we have 1 2 3 4 5, we have odd number of ones, 5 ones, so we can say P should be, or parity should be also 1, right? So these are the result basically we have after execution of this 2 line. Now, overall, for the RAM, how different portions are laid out inside RAM, we can discuss that now, and also we can talk about the register banks now. So we know that for our original version of 8051 we have 128 bytes of RAM, right? So starting address is 00H and the last address is 7FH, right? So from that, the first 32 bytes, these locations are actually called register banks. Okay, so we have register banks inside of these 32 bytes. So these are looking like this. Actually, we have 4 different register banks: register bank 0, 1, 2 and 3. So each of the register banks are containing 8 registers. So the registers we looked at earlier at the beginning, called R0, R1 up to R7, these are actually part of register banks. Okay, so you can see the same thing, R0 up to R7, and similar kind of thing can be seen for all of the register banks, right? We will see which register bank is used, how can we change from one register bank to another, but also understand all of the register banks or all of the registers we have for each of the register banks, they also have a specific address as well, starting from 00 up to 1F, right? So 00 to 7H is the starting and ending address of register bank 0. So in this way, for each of the cases we have 8 different locations, 8 different registers for register bank. So if we understand this much, now let us look at the next portion here. After these 32 bytes, we have this 16 bytes of bit addressable area. So in general, when we call any register, we are calling the whole register of 8 bit, right, to fetch the total 8 bit data. But there can be situations that maybe you need to specifically fetch 1 bit of data or store 1 bit of data. So for those cases, though, for those particular scenarios, we can use this region of 16 bytes. So they are bit addressable like that. Okay, all of the bits in this 16 bytes. So 16 different locations. In each of the locations we have 8 different bits. So 16 multiplied by 8, in total 128 bits of memory we have. We can specifically address bit by bit. And then we have, from starting from 30H to 7F, we have 80 bytes of general purpose memory. Okay, these are called scratch pad area. So if you fetch some data from your keyboard, from any input module, you can actually store those onto this particular area called scratch pad area. So these are the particular areas we have inside of 128 bytes of RAM of 8051, right? So we will specifically look on register banks because these are more important right now. So as we said that we have 4 different banks of registers, right? Register bank 0, 1, 2, 3. So whenever you actually start, initially you start, by default register bank 0 is selected in 8051. Okay, so that means this particular 8 registers are active whenever we initially start up. Okay, by default. But if you want, you can actually change them to any other register banks, right? So basically, if you want to do that, what you have to do, you have to take help of PSW. So do you remember we had, like here you saw we had RS1 and RS0. So basically they will help us to change the register bank if we want. So if we have put both of these values, RS0 and RS1, this is the LSB and this is the MSB. So if both of them are 0, so we have selected bank 0. If 01, bank 1, 10, bank 2, 11, bank 3. So in this way, we can select from bank 0 to bank 3 by changing the value of RS1 and RS0. which are part of PSW register. So how to actually change them? I think we can see that very soon, but before that, just look at a condition where register bank 0 is selected. So let's say our microcontroller 8051 has just started up and the default register bank 0 is right now selected. So for that case, if you use this kind of programming, so R0, R1, R2, obviously you can store different values onto different registers. But what you are actually doing is you are storing data onto 00 location. So R0 is basically 00 location in RAM. R1 is basically 01 location onto the RAM. R7 is equal to 07 location onto our RAM. So we can do the exact same thing if we want, directly using the address of the RAM. So this is called direct addressing. We can also do that. So this code and this code will give us the same result, because either we can use this kind of register names if we want, or otherwise we can directly use their address, RAM address, no problem. Okay, now as we said, if we change the register bank, then what will happen, right? That is the question. So here what they're doing, you see, set b psw.4. So we know that we had psw.3 and psw.4, right? So if this is 1, and by default we know that both of them are 0. Whenever the 8051 starts, both of them are 0, so register bank 0 is selected. So we can assume that this one is initially 0. So what we have done, we have selected register bank 2. This is the combination for bank 2. So if we have selected bank 2, then if we address or call R0, R1, R2, R7, these are actually part of bank 2 now. So basically these ones are the registers we have, right? So if we move any data to R0, what we are actually doing, we are actually storing data onto this particular location called 10H. Whenever we are moving a data onto R7, so this value is moving into R7, what we are doing, we are actually moving data onto 17H location. So in this way this changes, right? So you have to understand. Okay, so now another part of our internal RAM is stack, and very important one. So stack is basically a small section of RAM to store data temporarily, but the method in which we store the data is a bit different. So it works just like, you know, like placing books in a pile. So what you do, you place one book, then another book on top of that, then another book on top of that. In this way, one by one, the stack actually gets up, right? But whenever you are trying to get book from that pile or from that stack, you take the top one first, okay, then the next one, then the next one. So in this way, actually, whenever you are trying to get the books from there, you take from the top one first. So this is called last in, first out, LIFO, right? So in this way, we are going to see that we can store the data will be coming from different registers. It can be R0, R2, R3, whatever. From there, the data can come and it will be stored onto the stack. One by one, they can pile up. But whenever we are trying to fetch data from there, the topmost data will be coming first, then the next one, then the next one. That is the basic idea of stack. Okay, so one thing, there is one dedicated register intended for the stack, which is called stack pointer. So but this is basically one register to access the stack. So it contains address, and it will, this stack pointer will always point to the last used location of the stack. Okay, so basically one address. And because the length of SP or stack pointer is 8 bits, so possible values for SP is starting from 00H up to FFH. So more than what we need for our RAM. Whenever 8051 is started up initially, by default stack pointer contains the value 07H. So these are the things, just remember for now. We will look at one example which will clarify everything. Okay, so two things we can do using this stack is called push and pop. Okay, so we can push some data onto the stack, and just like a book pile, it can go up and up and up, and we can pop data from there, and the topmost value will be coming out, okay, one by one in this way. So first let us look at one example of push. Okay, so whenever push happens, another thing you have to remember, stack pointer initially starts from 07, right? The initial value stored onto stack whenever 8051 is powered up is 07. We know that, right? But whenever one push is happening, after each push, this stack pointer will increment by 1. So now we will look at the example here, and I think everything will be cleared up. So what we have in this code is basically, we are trying to save 3 different data onto 3 different registers, right? And then we can actually push this data saved onto these registers onto the stack just by writing codes like this. Push 6 means whatever data you have inside of R6, push that to stack. Then again push the data already saved on R1, push that to stack. So in this way, one by one it's happening, right? And here what we are seeing, we are actually seeing the data inside different RAM locations. So we know initially whenever 8051 is started, whenever 8051 is powered up, the initial value stored in stack pointer is 07H. So with that, let us start. So the first line of code is this. So we are just storing this data onto R6, then we are storing this data onto R1, then we are storing this data onto R4. But nothing is changing here because stack pointer or stack is not affected yet. Now look at the next line. So when we go to the next line, we have pushed the value we have inside of R6 onto stack. So as a result, you can see now 08H location has the value 25 because this was the value inside of R6. Am I right? And as well as this value of stack pointer has increased by 1. So right now the value of stack pointer is 08. So we know that stack pointer always points to the last used location of the stack. Last used location of the stack is 08H. So that's why stack pointer should be now 08. Next, let us go to the next line. Now you see, now we have pushed 1. That means we have pushed the value of R1 onto the stack, which was 12, right? So this value was stored here. As a result, stack pointer has increased by 1. Right now the value is 9, and 9 denotes the last used location of the stack. If we go to the next line, now we have pushed the value of R4 onto stack, which is F3, right? And now the current used location of the stack is 0A. That's why SP has incremented by 1 and current value of SP is 0A. So in this way it actually works. Hope you understand. Now we will look at pop. Okay, so it is just opposite of push. We can retrieve different data from the stack. As a result, the value of stack pointer will be decrementing by 1. We will see after each pop SP will reduce by 1. Okay, so we have the similar code just like before. So these kind of lines were there, and we had pushed 3 data onto the stack. Afterwards, this was the situation of the stack, and the stack pointer was 0AH, right? So if I now execute these 3 lines, which are actually pop 5 means currently on the stack, whatever value we have at the topmost level, take that value and save that to R5. That is what we understand by pop 5. Okay, pop 2 means the next value, whatever we get, that will be stored onto R2. So in this way, so let us try to execute those. So pop 5 should actually fetch this F3 data and store that onto R5 register, right? So let's see. You see this value is vanished, so which is actually saved onto R5. So R5 now has the value F3, and our stack pointer has decremented by 1. Previously it was 0A, now it is 09. Now if I go to the next line, after execution of that, the value we had here, look at this value we had 12. This value is now stored onto R2 because of pop 2, and our SP has decremented by 1. Then finally in this line pop 3, so the value we had here, the value was 25. So this 25 value is stored onto R3 because pop 3, and stack pointer has decremented by 1. Current value is 07, the initial value basically. So in this way push and pop happens. So whenever you push, the pile gets up and we have higher addresses, SP gets increased, and after each pop the topmost value gets stored onto a specific register. In this way, one by one, the pile gets reduced, stack gets reduced. Okay, now one problem is, as you know, by default stack pointer starts from 07H. This is the initial location stored in SP. So that means when we start storing data onto the stack, it starts from 08H, then 09, then 0A, 0B, in this way up to a higher value. So if we try to do this and try to push more values, you will see that there will be one issue, because you know, location 20 to 20 FH, these 16 bytes of RAM are specifically reserved for bit addressable memory. So that means you cannot use those region for stack. So that means the maximum, if you start from 08H, the final destination or the maximum memory location you can go up to is 1FH, because afterwards 20 comes. So in total you can have 24 bytes or 24 pushes you can do one by one. Afterwards you are going to go into the bit addressable memory, and that will cause some conflict, right? So that is one of the problem. Another problem is, we also know if we start with this default address for stack pointer, it will start from, the stacking will start from 08H. So if you remember from your previous discussion, let us look at that. Like here we can see that. So these are the 4 register banks we have. So whenever we are talking about stack and stack pointer starting from 07H, so we are going to start stacking from 08, then 09, 0A. In this way upwards it will go up to 1F. These are also part of register banks, register bank 1, register bank 2, and register bank 3. In any case, if you want to access or try to use register bank 1, 2 or 3 at the same time of using stack, that will cause some conflicts, because one will actually overwrite another data. So that can cause some problem. So this is called register bank and stack conflict. So these are the 2 issues we have. So how can you actually resolve that? That is the question, right? For that, what we can do is change the starting address or stack pointer starting address from 07H to an upper level value. For example, what we can do, we can change the value of SP to a value which is within the region of 30 to 7FH. So that means it will not cause any conflict to the bit addressable memory as well as the 3 register banks we have, right? So how to do that? We can use this kind of syntax to do that. So basically we can just call stack pointer and write a specific value, as RAM address. That's the idea. So we will look at this example here that will clarify everything. So as you can see, in this code, after the execution of the first line, we have actually done what? We have modified the stack pointer data, the data we have stored inside stack pointer, which was initially 07H, we have modified it to 5FH. That's the idea. As a result, now you see the stack pointer value is 5FH, and because of that, stacking will start from 60H location. So just like before, we will try to store 3 datas into 3 different registers, okay, but nothing is changing here. After that, pushing will start. So first push, which is coming from R2, so R2 value is 25. You see in 60H location we have 25 value, and stack pointer has increased by 1, so now value is 60. The next push coming from R1, value is 12, so 12 is stored here, and SP has incremented by 1, 61. Then again another push, so it is coming from R4, so this value should be saved onto 62, and the current value is 62, so SP again gets incremented by 1. So in this way, it is not conflicting with register bank 1, 2 or 3, or also bit addressable memory, because we have started from 5FH address, which is just part of scratchpad memory, general purpose memory, so it will not cause any kind of conflicts. So that's how stack can be used. Later on in the later chapters, we will see how this concept of stack can be used in different applications. So that's all for this lecture. Thank you.